In this video, I will present our paper entitled as End-to-End Deep Diagnosis of X-ray Images. I am Yernur Nurambek, Research Assistant at the Institute of Smart Systems and Artificial Intelligence of Nazarbayev University. In recent years, deep learning has demonstrated an outstanding performance in a variety of tasks ranging from recognizing handwritten digits to defeating the world champions in multiplayer online games. One of the areas that benefited most from the advances in deep learning is healthcare. That is why AI-based medical diagnosis is becoming highly commercialized, resulting in limited benefit for the developing world. We have leveraged the recent advances in machine learning and availability of public medical imaging datasets and created a free online X-ray diagnostic tool that determines the type of the X-ray and visualizes the abnormalities. Image processing and understanding using deep learning led to huge strides in radiology. Therefore, Turing Award recipient Geoffrey Hinton prophesied that we should stop training radiologists right now. In 5 years, deep learning will have better performance. However, our view is that deep learning will not eradicate radiologists, but rather enhance, augment, and reinforce their work. Our end-to-end X-ray diagnostic pipeline consists of 4 modules. The first module determines whether a submitted image is an X-ray or not. The second module classifies the type of the X-ray, and the third module runs the dedicated abnormality classification network. In this work, we only focus on the chest X-ray for abnormality classification. Finally, the last module outputs the visually interpretable heat map of the detected anomaly. Our work was heavily influenced by the advancements in the field. The ChexNet paper was written by Stanford researchers, and they claim that their model performs as good as radiologists. The authors of ChexNet used DenseNet 121 for chest X-ray classification. We further studied the architecture and built the third module based on this work. Another related work, Chester, the AI radiology assistant, is a web service that was designed to help radiologists to identify up to 14 different diseases. Their pipeline consists of 2 parts. In the first one, they check if the input image is a chest X-ray or not. If yes, in the second part, they give probabilities for each disease. They created a free website and hosted their pipeline there, so anyone with the internet access can check their X-ray images. DenseNet 121 is a deep convolutional neural network with 121 layers. It uses dense connections, meaning the network has direct connections from any layer to all subsequent layers. As a result, each layer has access to the previous feature maps, to the so-called collective knowledge. Another recent advancement in machine learning is RAdam Optimizer. ChexNet used RAdam Optimizer to train their networks. In our project, we used RAdam. RAdam is a new optimizer that was proposed in 2019. According to the authors, it shows an improvement in performance of the neural networks compared to Adam. In addition, the new optimizer is more robust to the initial learning rate. As a result, it requires less time to tune the parameters of the optimizer. The authors compared RAdam, Adam, and stochastic gradient descent optimizers for training ResNet neural network on ImageNet and CIFAR-10 datasets. The RAdam showed better results. We have conducted an extensive review of public datasets in medical imaging. As you can see, our model was trained on data that comprises 6 datasets, where 5 of them are radiographs and the other one is ImageNet, a dataset that resembles non-medical image data. So, for model training, we used the Catalyst framework for PyTorch from NVIDIA DGX-1 machine. As we already mentioned, the pipeline consists of 4 modules, where the first one distinguishes X-ray images from non-X-ray. To do that, we used joint data of 5 medical imaging datasets versus ImageNet. All the images were converted to grayscale and resized to 224 by 224 pixels. We used DenseNet 121 as a classification deep learning model with RAdam Optimizer. The same machine learning model and parameters were used in Module 2, where the module's task is to classify an X-ray type of an image. The model classifies an image from 14 labels that were accessible in datasets. Module 3 in our pipeline is supposed to identify what kind of pathology the X-ray may have. For now, only chest X-ray analysis is developed. However, we continue to expand our system. So for this module, we use chest X-ray 14 dataset of National Institute of Health, which contains 14 labels of patients with pathologies and one for the healthy patients. The model is also DenseNet 121 with similar parameters to the former two modules, with the exception of Optimizer. We used the RAdam Optimizer since it demonstrated accuracy improvements. And for the last module, we utilized gradient-weighted class activation mapping, or GradCam, to visualize the last convolutional layer of the third module. Now, let's discuss results. On the left side of the slide, the confusion matrix of the first module is demonstrated. As you can see, the model can classify radiographs with accuracy of 98.7%. On the right side, misclassified images are shown. We can notice that X-rays with metal implants are being confused as not X-ray images, whereas, for example, a bathrobe, which slightly resembles a chest, is confused with radiographs. Here you can notice that Module 2 classifies 14 X-ray types with an accuracy of 97.6%. This slide demonstrates the results of our deep learning model in comparison to previous works. You can notice that we obtained better results in classifying atelectasis, effusion, consolidation, edema, fibrosis, and hernia. In this figure, you can see the input and output images of the pipeline side by side. The system successfully demonstrated features of effusion using GradCam. If we combine all the accuracies of the modules, we get 65.9% overall for our pipeline with chest X-ray for Module 3. Here we demonstrate the backend details. The image is first uploaded to a web server, which is then passed to DGX2, where we run our Python script with inference models of the pipeline. The Python script is wrapped into Flask web framework, which in turn runs as Docker container. After being processed in DGX2, the Python script returns JSON with all the parameters of the image to the web server, where the result is shown. When we upload chest X-ray, the heat map image is base 64 encoded to JSON. However, in this case, since the modules 3 and 4 of the pipeline are being developed, we see only the name of the X-ray type. This demonstration shows how you can use the end-to-end deep diagnosis of X-ray images tool. First, we try to upload a random image. The system tells us that it's not an X-ray. Now, let's try to upload an X-ray of a hand. Since for now the abnormality detection is set up only for chest X-rays, we get only the type of the X-ray as an output. We upload a chest X-ray of a healthy patient and see that the system does not find any abnormalities. Now we upload several chest X-rays with different abnormalities. The system outputs the names of the abnormalities along with the confidence scores and heat map images, visualizing the abnormality. This work demonstrates that a data-driven, computer-aided diagnosis has a significant potential to assist physicians as a decision support system. 96% end-to-end accuracy of the first two modules and 0.84 AUC score for the third module means that this tool can be used by individuals living in developing countries to get preliminary results for their projectional radiography examinations. Please visit the SciENS website to try our system. In future, we are planning to explore pathology detection and the rest of the X-ray types and add the mammography modality to our system.